anyone coming? Anyone else? We'll get started. All right. So my name is Campbell. I'll be your tutor for the next couple of weeks for the FEA portion of MD2. What we're going to run through is mainly SolidWorks tutorials. But one thing to keep in mind is that each one of these tutorials is trying to teach you something, whether it be one of the principles behind FEA itself, one of the limitations, one of the problems, or a way to make your life easier if you're running low on computing power. I know some people don't have fantastic computers, and this can be quite resource heavy. The main trade-off between higher accuracy is computation time. Places like NASA have entire warehouses dedicated to computing finite element analysis for their rockets. Same as Formula One, they've got quite powerful computers, which they specifically dedicate to stuff like this. So it can get quite resource heavy, and the stuff that we're doing mainly for the final assignment can take quite a bit of time, up to half an hour per simulation if you don't have a fantastic computer. So there's good trade-offs with minimizing the actual simulation difficulty to make it take a lot less time. But personally, I've had a lot of experience with FEA through my involvement with motorsports. I've done a bit of research at UTS, so I've done a bit of design and optimization for different projects, and a couple of other things around the uni. So I've had a fair bit of experience with it. It's very versatile and very useful. Hopefully you guys get a lot out of this, and feel free to swing me any questions. We'll get into it. So what is FEA, or finite element analysis? It's called finite element analysis because what it does, excuse me, is breaks your model up into little elements. So you can see on the right-hand picture here, it's broken the part up into what's called a mesh, and your mesh is comprised, in this case, of tetrahedrons, which are small triangular pyramids, that it can warp and change the shape of to match the actual geometry of the part. There's different types of elements. SolidWorks specifically uses tetrahedrons, but when you get into more complex programs or more complex analysis packages, they have different shaped elements, which have been outlined in your lectures. On that note, lecture 1, very important. It goes through some of the basic principles and some of the problems with FEA itself. Given that it's a mathematical solution, there are occasions where it likes to divide by 0, which is what you'll be looking at today. See if I can do this without looking. I'm going to try and draw with my mouse. So you've got stress equals force divided by a cross-sectional area. So very basic run through of one of the main limitations. At this point here, in this model, this one here, you've got an internal square edge. You can dumb it down to look like this. So you're looking at this corner here. As you approach that internal square edge, your cross-sectional area is approaching 0. As your cross-sectional area approaches 0, this stress value approaches infinity. So you theoretically have an infinite stress point. Now, the solver will calculate it as an infinite stress point. So you'll get a much higher stress here than you will get in reality. So when you're working through the tutorial today, there's a little method at the end. You'll run through the tutorial itself, and then it'll ask you to plot your results in Excel. Do that, and then let me know, and I'll run you through the process that you use to actually determine whether it's doing incorrect math and creating what's called a singularity. So we'll go through that when we get to it, but it is very important. Cool. Who can use FEA? So probably the main use that you guys will see is mechanical analysis. So stress or displacement are probably the two big ones. And these are what you use when you're trying to optimize a part, you're trying to cut a bit of weight out of it, or even just verify your design and make sure that it's going to satisfy the use case that you're designing it for. Electrical analysis. So there's a lot of thermal analysis on electrical components. There's a lot of other things you can use it for. You can do heat exchangers, so you can simulate the actual airflow through a heat exchanger, which I have a couple of images of a bit later. And civil will use it. So civil can use it for the design of cityscapes, and they can look at the actual airflow between buildings, which is very important when you're trying to design, say, a new building in the CBD. You don't want it to create a massive Venturi effect between buildings and have obscene um, wind speeds between them. Because you can imagine if you're a pedestrian walking on the street and there's constantly a massive gale through that particular corridor, then you're going to have a lot of issues. There's a lot of others that you can use it. These are probably the main ones. But yeah, we'll cover a couple. So why use it? Why use FEA? Previously, before this software existed, what you had to do was design something with hand calculations. I mean, you still do have to do hand calculations before, but you spend a lot of time actually calculating the stress in each component and where the stress was concentrated, um, which took a lot of time and a lot of resources in terms of um, engineers. So what you can do is you can actually sit down, calculate the forces, input them into the simulation software, work out where the stress is, where the stress isn't, take material away, and you can do iterative design before you actually manufacture it. Of course, you should always um, manufacture it and then physically test it as well, just to verify that your simulation was correct. Um, but it saves a lot of time in terms of iterations. Different uses of FEA. So what we'll be mainly focusing on is linear static. So that means we're assuming that the material is always in the elastic region of its stress strain curve. So regardless of the amount of force, the amount of stress you put it under, it will respond elastically. You can do dynamic. Dynamic is when you take the material past its yield stress and you get into the plastic deformation. A lot more complicated, a lot more difficult to set up. You've got to have a really good material model. So what we mainly focus on is linear static. We do some dynamic stuff, which is the frequency analysis, but that's a bit later. But we do mainly focus on linear. Topology optimization. So this is kind of the next step past your mechanical analysis. What this lets you do is the simulation itself will remove any low stress elements that are have a stress value below a certain threshold. So you can say if anything's got 50% less than yield stress, take that away, and you can get some really weird looking, really cool weight optimized components. And I have a few examples of that to show you. Frequency analysis, so looking at the natural frequencies of a body. This is very important when you're designing a dynamic system. So again, I've got a few examples, but you can imagine a car driving down the road. If your natural frequency of the vehicle matches, say, the frequency of the road, you get some excessive vibration, which can cause extra fatigue and also insane peak loads, which can cause issues in a mechanical system. Thermal analysis kind of speaks for itself. You're looking at the transfer of heat through a body itself or through conduction to a fluid. And then you've got CFD. So CFD is kind of its own thing. It is FEA in its essence, but it uses different solving methods to the mechanical stuff. Mainly because you're actually looking at the fluid around a body, not the effect of the body itself. I haven't personally done any CFD, but if anyone's very interested in it, I'd be more than happy to point you to some good resources or to someone that can actually help you out with that. So mechanical analysis. The one thing that you need to look at, this has a constraint, it has a material, and it has a load. So your constraints and your loads are your boundary conditions. If you're looking at this as a problem that's trying to be solved, it's a bunch of equations, and you need a starting and a finishing position, and then it solves everything in between those. So start with a constraint. So this face can't be moved. You apply a load to the end of the spanner, and then this is the von Mises stress that is demonstrated once you apply that load. Now you get the same thing here to this conrod. This is a conrod out of an engine. This is a really weird load case. That's not something you'd usually see. This is a two-force member. So you'd usually have the load going parallel to the I-beam down the center. You don't usually get a lateral load in a conrod, but you can see again the stress analysis through this beam in bending. This is topology optimization, like I was talking about before. With the up and coming technology of 3D printing, it allows for some really insane designs to actually be manufactured. So this is done and manufactured through traditional machining methods. They've then done a stress analysis on this original part. They're obviously trying to save weight. They've put some manufacturing constraints on this, saying that these holes have to be there. There's no exceptions. Without those holes, this bracket doesn't work. And then you can see this really strange organic structure that's left over. And this is what the solvers actually come up with to say, yes, this will do everything you want it to. We've removed X amount of weight. And then you can see on the left-hand side, these are the steps that they've taken to remove weight. Now, you could actually manufacture this through 3D printing. You couldn't use traditional machining methods. So you can start getting some really, really cool stuff. Frequency analysis. So again, I was saying before, you've got a bit of a gear on the left-hand side or a turbine. As this thing rotates, you want to look at its natural frequencies, because this is not something you don't want your natural frequency and your operational frequency to be the same. You get excessive amplitude in the force for your gears. And then on the right-hand side, you've got your vehicle. So you can imagine if you're driving down the road and you start hitting a few bumps, and then your vehicle starts doing this, you get excessive movement in these low support sections, which is obviously very bad, because you do not want your vehicle to do this. It should be rigid enough that you can drive it down the road without a problem. So understanding the natural frequencies of a system is very important. Thermal analysis. So this is done in a program called ANSYS. So ANSYS is a simulation package with many, many years of development. It's probably the industry standard for everyone. And you can do things like this. So you can simulate the heat sink of, say, a computer processor across the board, or you can do a heat exchanger, and you can see you've got heat going in on one side, or cold air going in, heat coming out, and hot air going in and cold air coming out on the other side. So there's a good demonstration of two different use cases for heat exchangers there. Finally, CFD. So this is probably the coolest one, the one everyone gets the most excited about, mainly because of its involvement in the design of race vehicles. As you can see, you've got the Ferrari Formula One car, and you can see the streamlines of air going across it. And there's airspeed across the surface of the vehicle, as you can see, shown by the colors. That's everyone's favorite thing, but you can also use CFD, as I said before, in cityscapes. Like I was saying, you've got these Venturi effects down between the buildings here, so you can imagine that these airspeeds are quite high, and that's something that you try and avoid when you're designing a CBD. So Civil can use it for things like this as well. And then, of course, my personal favorite. There's a lot of people that do CFD on really weird stuff. This one's a cow. Absolute waste of time, but it's hilarious to look at. I've seen a few people do CFD on. I saw Santa's sleigh, and I've seen a hamburger. People love to use their time and waste their resources for stuff like this, but it's a good laugh. So the golden rules: if you put garbage in, you get garbage out. What that means is, if you don't understand what you're putting into the analysis in terms of forces, constraints, material, the result that you're going to get is going to be just as bad as your inputs. If you make assumptions for your calculations in terms of your free body diagrams, your expected max loads, anything like that, that will be reflected in the simulation, and that's something you need to keep in the back of your mind. FEA is a tool. It's not going to give you the end result. It's not going to tell you that, yes, this is going to work. It's going to give you an idea of roughly how it should behave and roughly what the stress will be in the component. So take everything with a grain of salt, and that's why I have this quote in here: all models are wrong, some are useful. So everything you put in is going to be taken with a grain of salt. It's going to be useful for you to make a decision on the design itself, but it's not going to give you an answer. So keep that in the back of your mind as well. Basically, for SolidWorks, what you need to do, when you get into simulation, you'll have this new study advisor. Don't use the study advisor, use new study. And then across the top of the screen, there's a bunch of buttons. I usually like to start at the left and work my way across. That's the easiest way to set it up. It's very nice. But of course, the SolidWorks tutorials are going to step you through it. Number one, define the problem. When you're defining the problem, this is a free body diagram. You look at the actual part itself or what you're trying to design for, and you define the system that you're trying to analyze. You then create the model, which you either have one already or you're going to design it yourself. Choose the type of analysis. So like I said, we're going to be using static mainly. Define the loads and constraints. One thing that's not in this is define your material. You have to have a material. The way that SolidWorks calculates the stress is it looks at the stiffness matrix of the component or the material. It then applies a force to it, looks at the displacement. Based on the displacement, it can work out the strain, and then using your Young's modulus, it can calculate the stress. Then you can define your loads and your constraints, run the analysis, view, interpret, and evaluate. This is very important. You have to interpret your results. It's not just going to give you exactly what you want. You have to make it a usable result. And I will go through that as well. The next thing, what I want you guys to look at this week, you should be in week 8 to 11. So subject documents, week 8, 11 FEA. Scroll down, tutorial 1. Now the parts are here if you need to download them, but they should be available on UTS. It should be available through SolidWorks. You shouldn't have to download them, but they're there if you need to. Run through what it tells you to. This is the tutorial that you'll be working on. Once you've finished this tutorial, there's a few steps here. So read this, and I want you to plot the different responses to the different degrees of freedom. I'll do this as well, and just before the end of class, I'll give you a run through as to what this actually means and what it's actually trying to teach you, which is probably the biggest point that you'll get out of today. What this course is trying to teach you is not how to use FEA, it's what it does, why there's problems with it, but again, why it's useful. Cool. So, number one, SolidWorks, and you want to go to, should be help. Not there. Anyway, so you should be able to click on SolidWorks, there'll be a help button, click tutorials, and you should be good to go from there. Any questions? Anything? Not one question. Beautiful. When you do import the part or open the part, down here are little tabs, just like in Excel. There should be some set up already. So you don't need to do the full analysis yourself. You don't need to set it up. You can if you want to, but most of the tutorials have predefined simulations set up, ready to go. So just make sure you go down here and you click ready. Cool. Now I'm going to split you into breakout rooms, probably 3 groups. Yep, 3 groups of 7, and we'll go from there. I'll come around periodically and you can ask me any questions if you get stuck. Awesome. Excited, ready to go. Happy Wednesday, Thursday. It's Thursday. Happy Thursday.
Oh shit, it is Thursday, hey.
Oh,
Yeah.
I just lost today.
SolidWorks stream. Marketing group.
I'm waiting for SolidWorks to start.
You don't have the start already.
Nah, it's a bit lazy. Sorry.
So wait, are we supposed to like do all these things?
No, read the
I'm
tutorial
reading
document.
it. It doesn't say. Oh yeah, there's little. analysis.
I
like,
literally read out which one you had to do.
I wasn't listening. I was, but like there was a lot going on, you know.
I even had it up on my screen.
Yeah, but
You didn't have to listen. You just had to look at it.
Right, analysis of part. The bracket
Mate.
made our step. Oh. Okay, I don't have to read this first bit, do I? I'll just open the part.
All right, I'm gonna go check on everyone else. I'll be back.
No worries.
Don't leave. No.
No.
Is anyone else there?
Yeah, is it? Are you guys actually like around, or are you just
Should we
hiding?
just go back to Discord?
Oh, I'm so tempted. Raise your hand, guys, if you're like here, but you just don't want to talk.
Well, I think that they must be here because they clicked the breakout room. So
Yeah, that's true.
no hiding. No hiding from Mr. Campbell.
Nah.
Click here to open.
Pardon me. Oh, SolidWorks is open. Do you want me to share my screen? I'll share.
Up to you.
I'll share. I'll put it over here so it's in the recording.
Yeah, that's actually a good idea.
Okay.
Edit material.
Open. Downloads. Tutor 1. Solid part, I'm assuming. Oh, there's the tutorial notes.
Yeah.
Oh, look at
left plane. Click.
Okay.
Steel. Alloy steel.
Help. SolidWorks tutorials. Oh, Jesus Christ, stop doing that. I just realized that I'm sharing the wrong screen.
Mate, close some tabs, please.
Nah, I like my tabs.
He's recording the class for you.
Is he?
Yeah.
Yeah.
Legend.
James has got the following. Alright.
You see
Alright.
famous, is he?
Yeah, he is. In the MD2 bar.
Mate,
Create a static
he's been famous
analysis.
since we started science, mate.
Yeah, that's true. Simulation. Alright. New study. Under general simulation, click static. So all these options are already done. Like everything's already
Yeah.
selected.
Most of them should be because it's the standard. It's the most common one that you use. Most.
I give it a name, a different name.
I don't care. What?
Name.
Oh, I forgot to give it a material.
Static analysis 1.
Oh, alloy steel, that's fine.
Yeah. But you've got to define a.
Oh.
In your study, you then define a material. So just
Static -1.
like I said before, start here and move your way over to here.
So we go right to left.
Yes.
So on a static study, yes.
Yep.
Yeah, you had a lot more options than me. Indicating
Apply material.
I've assigned a material. Okay, applying the fixed constraints.
So the material is kept separate from the material in the model. The reason is you can actually change your material and iterate your design without affecting the original model.
Oh shit. So, yeah, no, I sucked. Whew. Okay.
Okay.
Click down arrow on the fixtures advisor.
Come and solve X. Not that hard.
You have a weapon. Don't you have a weapon computer?
Apparently not. Let's check.
Hell, man.
What's going on with Task Manager? Oh, there she goes. Fuck me dead. Close that shit. Alright. Oh, this is like we did last. Fixtures.
Okay, in the graphics, click on
Is
the
it
faces.
fixed geometry? Yes. Look at that. Look at that like little pre-shoot we had last night. It's like all
Nice.
coming back to me.
We'll come back to you.
Okay, so we want a
Let's
fixed
check on
geometry
everyone else.
here and here.
You just click the faces, hey, and just leave them fixed geometry. Yeah.
Yeah.
Sweet.
Applying pressure. External loads.
Click on the down arrow. Pressure.
I'm gonna keep it in newtons per meter squared. Or do I put it in I'm gonna put it in megapascals because you know this is how we roll here. How many megapascals do we want? So now I'm gonna do
1,000.
1,000. 1,000 psi. Let's convert that.
Alright.
6.89 MPa. Cool.
Using MPA.
Yes.
Alright, I'll do 1,000.
Where's our boys? Where's our boys? Darren, Yeon, Kai. Jeon. I think I said that wrong, sorry. Oh well.
What if one of them's a girl?
True.
Where's our homies?
Where's our team? There you go. Look at that.
Maybe they don't have voices.
Maybe.
Maybe they're like mutes. Can't actually speak.
That's possible.
I feel like 1,000 megapascals is a lot. Oh fuck it, we'll just see what happens. Take it with a grain of salt, you know.
How fine do we want this bad boy? Who cares? Okay.
Setting mesh. Oh, you're too fast.
Mesh in progress.
In the
Mesh.
simulation tree, right click mesh.
It's
Create
meshed.
mesh. So
Okay, let's run it.
we don't know how fine did you do it?
What's that?
I'm doing it like kind of a bit to the right of the middle.
Yeah, I do the same. Look, it's bent.
Ooh. Do you look at that?
Now, what was the thing you were showing me last night? Is it chart options?
So run this study. We didn't do anything to shell, did we? Excessive displacements are calculated in this model. If your system is properly restrained, consider. Did that pop up for you?
What's that, sorry?
Did like this when you clicked run simulation? Does it excessive displacements are calculated in this model? Where's Mr. Campbell?
Cam man, press the help
Message him
button.
on Facebook. Oh, can we? Is that actually
Yeah.
a signal? Where's the help button?
The host has been
Oh.
invited. Can I just keep clicking it?
Oh,
Oh, he's
Campbell.
here.
Hello?
Um,
Up, mate.
It came up with when I did run the study. It's saying, oh shit, where'd it go? It says excessive displacements were calculated in this model. If your system is properly restrained, consider using large displacement option.
Can you share your screen?
All right. Oh, this is all going to be in the recording.
Most likely going to be your fixtures.
Can you see?
Yep. Your pressure's meant to be in PSI.
Oh, okay. Like, I was like, isn't I just did megapascals for that. But...
Yeah.
You didn't convert it.
It's probably just too much force.
Yeah, I was thinking it was too much force. But...
6.89 megapascals.
We'll be American.
145,000 PSI. So excessive displacement because you folded it in half.
Yeah, gotcha.
Instantly.
All right. Sweet. Cheers to that, Matt.
Good busy.
I'll let you share again, James. Sure. I think that's a good example for the video.
Yeah, definitely.
Remember to like and subscribe, guys.
Share, like, and subscribe. Subscribe to my OnlyFans.
Hit that bell so you get notifications.
What was the thing you showed me here yesterday with like the changing the stress plot options?
Right click on edit on the graph.
I've done that. It's here on the left.
Oh yeah, right. Yep. So make the bottom one 0, and the top one, click the arrow and make it your yield stress. Yep, and then click show max. Can do show max if you want. I usually don't because it moves. Change scientific down the bottom to general, and then go to settings, and go where it says continuous. Change that to discrete, and then change your boundary options to mesh. Then tick.
What's this show or hide mesh button?
Why didn't that update?
It did that?
No. Didn't change your scale on your graph.
How do you show like the stresses again?
Double click on the results.
Double click. Ah, yes. Wait.
Yeah, so it does change it, but like it goes. So 6.2.
No, because it's still in Newton per meter squared. Change it to MPa. So in definition. Yeah, go MPa. Yep.
Right.
It's your standard stress units. Makes it a lot easier.
But it's still. What are you doing to me? There we go. Ha.
Ah.
I'm gonna change it to MPA now. Whoa. Look at that. Infinite stress at the corner.
Is it?
Nah, it's not infinite. It's just like a red dot.
Yeah, but is it a singularity?
That's where the singularity would be.
If it is
Like-
one.
I'll zoom in.
How do
for you.
you know it is one?
I don't know if it's singularity, but it's in the corner. I don't know
Yeah.
how to check.
Keep doing the tutorial, it teaches you. And then I'll explain it.
under display. Set units.
Right, I'm gonna check on everyone else.
Sweet. Okay. Click on plot tools. Animate. Oh, cool.
one's down here. Property manager, select Max von Mises stresses. Oh, right click results. Go define factor of safety plot.
What one are you up to?
Assessing safety of design.
Sure. Smashing through. Strain. In the simulation tree, right click. Results. Define a factor of safety plot. You've done that, yeah?
Yes.
Max one mistress. Oh wow, it's all red. Is that good or bad?
I think it's bad. So how's this bit work? Click the regions.
Yeah, I know, bro.
But it's all red, but in here it shows blue. What the hell? Okay, I'll just go automatic and see what it does. Areas below, factor of safety. Oh, there we go. Okay, that's it there. Right. Makes sense. Do you see on my screen? Do you see?
Yeah, nice.
For a better view of critical regions of the model, you may need to hide the restraints and pressure symbols. No, it's fine. Click report.
Oh yeah, just did that bit you just did. For a better view of
Contact information, sensor details, beams.
Oh,
Select a report section, update information. No, that's fine. Hello.
how's it going?
Good.
Alright.
All the other breakout rooms are silent.
Just like ours. Same.
Crickets.
If you two noisy lads.
It's yeah, so we have like the part we did the bit where we show the parts below minimum factor of safety, and it's like those corner bits that you're talking about. Is that what you meant by like it's got an affinity, or that just means it's below the factor of safety? It doesn't necessarily mean affinity.
Yes.
Okay, double click the factor of safety icon.
The tutorial document that's on UTS Online, it has a method. It teaches you how to check for a singularity.
Right. Double click the factor of safety icon under results to display the factor of safety plot again. It's not just. Oh, wait, I'm pushing that wrong. There we go. Oh, then just click report. Okay, yes, report.
So a really detailed report. It's pretty impressive, actually.
Really? In the dialog box.
Here it
upload
is.
Report sections.
Do you like the header, Cam?
Yeah.
Close section. Connector definitions. Contact information.
Yeah, that's quite impressive. It's pretty cool.
Yeah, it does it all for you. It's great.
Beams is loaded as a select the report.
Is
Select it.
is this the whole? Is that the first shoot done? Or is there more?
Oh, there's more.
What's it mean by like select a report section, then update the information under section properties? Oh, is that just like if you want to add comments? Oh yeah, I didn't read the other bit. You can add comments. Okay. Header information. Designer. Should I put my company in there?
After completing the first analysis of part, complete the following extra exercises to help you think about things and show you a few things the tutorial doesn't.
There you go.
In results, right click, define my stress plot.
I'll be back.
Didn't we do this with you? Oh. Don't leave us, Cam.
Show report on publish.
Oh, we did all that. That's fine. That's cool.
Did you change the scale of your MPA? Or you just left it like how did it?
Oh, do you want to see how to do it?
Oh no, I think I know how to do it, I'm pretty sure. But like, I was just wondering if you did. Oh, it's a nice report, eh?
Yeah, it's
I'll
pretty
do it
cool.
next time. Okay. Sweet. What next?
I'm not
Close
putting.
report window.
I'm not going to put anything in that table.
To change the default.
If time permits or in your own time later, complete a static analysis of a sheet metal part tutorial.
What's it mean by to close the report window? There's no report window showing. I'm confused.
What's this?
It's like to close the report window, click X, but like the report window closed, I thought. Oh, save part. Save.
All right, here we go. We're going to do
Okay, we're gonna do the next
the
bit
sheet
now.
metal.
Okay. In results.
Static 2. It's fine.
In results, right. What's R and B? Click. Right middle mouse button. What?
What's this?
Never mind. It's like R and B click. It's like just right mouse button click. Okay. was like, right middle mouse button. Okay. Okay, change units to MPA. I'm pretty sure it did tell us to do that in the cheat.
Where's this simulation study tree? Right click, shell study, select properties.
What is this?
You what, man?
This is not the tutorial.
Yeah, it is.
Oh, listen.
Yeah, it is.
Did you do the plotting of the degrees of freedom versus stress in Excel?
Yes.
You really need to do it. I'm not kidding. It's like the most important thing that you do today.
Okay.
So go back to the first tutorial. Yeah. And to plot the degrees of freedom versus stress for different mesh sizes. What the tutorial document from UTS Online tells you to do.
Okay.
Yeah.
I'm gonna have to do all this again.
No, you just do it down the bottom where it says ready.
Oh yeah,
There.
I clicked it.
Yeah. Now if you should just be able to, why is it empty? There we go. Now you can just click run and it's finished.
Right middle mouse button.
Cool.
Each time you set up a new study, it ends up as a tab down the bottom there. You can see the other two that you started.
Discrete.
Yeah.
The static 3 is probably the one that you did.
Yeah, it is. Okay, cool.
Why have you got 6.8? Did you convert it?
Yes, I did.
Fair enough.
The location of the max stress is in that little corner. That's where I expect.
So when you're looking for a singularity, you always want to check the same spot. So you're looking at a point of interest, not wherever the max is. You should be looking at a point of interest.
So it should be that corner. It's like just above the corner.
Yes. Now,
So it's
why
not-
is it just above the corner?
Cause...
Think about it, and I'll explain it to you later.
No. Just tell me the answer now. Just tell me the answer now. Because well, the area is 0, but the area is also 0 down the corner.
The area 0 only at the corner.
Huh?
So why is the max stress above it if that's where the highest stress point will be at that internal edge?
Magic?
Yes, it's magic.
Let's keep going.
Keep going. I will explain it. I'll do I've done this whole thing and I've done the whole plot and everything we need. I can explain it to you at the end.
I'd hope so.
Yeah, fair enough.
Right click. I really wish you just wrote right click and not R&B.
Huh?
I really wish you just wrote right click on the tutorial and not R&B.
Someone said that yesterday as well.
Yeah, it's just like R&B. It doesn't.
Yeah, right mouse button.
Yeah, I don't know. What if I'm not using a mouse?
Alright. If you're not using a mouse with SolidWorks, you're doing it wrong.
I'm using a joystick.
You actually.
No, but I could.
Have you seen the you can get mice that are actually for CAD and it's like a 3-dimensional mouse?
No, that's
It's like
cool.
It's like
I
a
think I've
ball
seen it.
and you can like
Yeah,
lift them up
yeah.
and down and stuff. Yeah, it's awesome. Apparently they're really, really good.
It's hard to use, weren't they, though?
No, apparently it
At
makes
first?
yeah, it takes a little bit to get used to, but once you're used to it, apparently like it's life changing. Especially if you're doing like a lot of design.
Mm. No, you know when it says click on the mesh, select details, note the information provided. Do I have to like copy and paste that, or just look at it?
What?
It says like look at the mesh details, and then just it says note the information provided. Do you like want us to like copy and paste that, or just look at it?
It's all good.
I guess so. Right click results.
Right, we're back.
No worries. Solve the messages.
Oh, I can't be bothered doing the Excel thing. I should.
Definitely do it. Wait, do we have to do this analysis multiple times? Or?
Yeah, so like you run it
Yeah.
and you get the values, run it, get the values, run it, get the values. Which is like, I don't want to do it.
Let's do it. We'll probably have to do it for our assignment, I'm guessing.
True.
Let's do how about we do it together in Excel? So we can do like half the amount of times. You feel?
What's that, sorry?
Like we'll get a live Excel going.
Oh, yeah. I'll
What's
try.
that? I mean, fuck, are you already all the way down there?
What's that?
Element type. No, just like, how did you get all the way down to that? Oh, no, it's just... Never mind. Oh my god. What does it mean by like element type? Like tet? Tet 4, like what's tet?
Tetrahedron.
Okay.
If you'd gone through the lecture, you would know that.
Man, I don't have time for that, alright?
You do.
I actually don't.
I'm staying up all night on Discord.
Mate, that's like, I get home from work at like 5 o'clock. No, like 6:37. I have about 2-3 hours to do this JDR, and then that's about it. Go to sleep, wake up at 6, go straight to work. Rinse and repeat.
Oh, excuse me. Wow.
Excuse Mr. Campbell. Oh, you already started the book. Alright. Too quick.
Just keep up, mate.
So, when it says like, it's got like, why does Tet 10 have mesh control? Like,
We'll get an email.
Just close my one.
Oh, I just sneezed like 6 times in a row. Oh my god. Oh, I'm back. Do you know the difference between a Tet 10 and a Tet 4?
Tet 4 has 4 points. Tet 10 has 10 vertices.
Yep. And then there's a difference in the way that they're solved too.
Right.
Allow me to demonstrate.
So this is a Tet 4 that we just did. Like, it doesn't actually tell us anything.
No, so by default you're doing Tet 10s.
Okay,
This
so,
is that's what a Tet looks like, right?
okay, yep.
Tet 4 has 1, 2, 3, 4 points. Make sense?
Yep.
The stress is calculated at the center of the Tet, and then interpolated to each of the vertices. Yeah?
Mm-hmm. Alright, so calculate the center and then
Yep. and then
interpolated between every vertex. Okay.
the vertices are shared between each of the tets that surround that vertex,
Yep.
and then averaged. Make sense?
Okay. Yeah. Gotcha.
Now, because you've only got 2 points, to calculate the displacement of these 2 points is a linear equation, right?
Which 2 points? I don't know. I can't see what.
Like 2 vertices, like say this one and this one.
Okay. Yeah.
You've got 2 vertices, so it's a linear equation between the two.
Yep.
Tet 10 has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's got one halfway along each edge. Which means if you've got 1 point here, 1 point here, and 1 point here.
3.
Yeah?
I'm lost.
I'll draw a new one.
I'll just Google what a Tet 10 looks like. Might be easier.
Well, it looks the same, but you've got, instead of just one on each edge, one on each corner, one on each vertice, you've got nodes halfway along each edge as well.
Gotcha. Yeah.
Okay.
I was missing the ones like going up above towards the top one. Alright, yeah, that
Yep.
makes sense.
So if you've got nodes along each edge, you've got a line that looks like this.
Yep.
Which means that you can define it using a
Sinusoid.
no, not a sinusoid, but a curve. So your edges are no longer limited to being straight. You can actually have a non-linear equation which defines your edges.
Mhm.
So it becomes much more complex, but you can more easily model curved edges.
Okay. So Tet 10 is
sense?
better than Tet 4.
Yes, but it's harder to compute.
Gotcha.
Do you like what I've put up for you there, Cam? The
Yeah, it's
background?
fantastic. Hit 15, that's cool. X's,
Okay, so
also called cubics. And then there's octa something as well. Cool. I like that.
Sweet.
why is this not? I want to download this.
What do you want to download?
Alright, I'll be back.
Sweet.
Thanks, Cam.
Why is do I have to do this all in the Windows version, like the the internet version of Excel? Is that like how you've been working on it?
No, like you can open it in normal Excel.
Oh yeah, no, there's a bloody button at the top. What's that? Sweet. Alright. So, Jet 10, I'm guessing. Let's record the degrees of freedom.
Actually, I'll do this.
Again. Details.
Oh, oops, I've picked the wrong one. Of course I have.
Oh. Results. Solver messages. Oh my god. That's right. 68571. Okay. Three, 7, 9. E to the 10. No, e to the 3.
I've got the min. If you look at my screen, actually I can just pop it in. Is that max or min or the default one you just put in?
The one I've put in is the max. We don't need min, do we?
Yeah, we do.
Where's that on the table?
There.
What? I'm confused.
It's the in the thing it says where is it?
What do we have to do again? We go the. If we just change the course, if we just change it to course and rerun it, that's like all we have to do, right?
Yeah, so that's what I've done. That's what this is here. I thought we had to go middle of the road as well.
Okay, so that. Okay. Okay, well that first one was just when I rechanged the thing slightly. Like it wasn't actually in the middle. I'll do it for the middle. Well, I'll do it for the finest then. Run the study. Do we have to change all those bloody settings again? No, we don't. Sweet.
Okay.
Looking.
So we're supposed to do like middle row, middle mesh, finest mesh, and coarsest mesh. Yeah, this table crap. You're a genius.
Usually, you need more than 3.
Wait. Why doesn't everybody copy the number?
What are you doing, James?
What's that?
What are you doing?
Breaking stuff?
What are you trying to do?
Get the
Max?
max, yeah.
So get out of that. Click here. Click probe. And now click on the spot you're interested in.
How do you know that's the max?
Well, you're not interested in the max, you're interested in that spot. Yeah? Because the max can move. If all of a sudden somewhere else on the model becomes higher, the max will move. And you're not interested in wherever the max is, you're interested in the same spot every time you run it.
So
Because you're wondering whether that spot is a singularity.
What was the point of sending the max? Like setting that max thing. So we're not actually supposed to take that max value.
As long as the max is in that one spot, then that's what you need.
The max isn't. It's like just above that spot.
Well, I mean, it's close enough. As long as it's in that hot spot. Because remember, it's an averaged result.
Got it. How do you show the max displacement? Do you have to change all those settings again?
You can no, you just double click to
Displacement?
on displacement, and then you can use your probe tool again. What are you noticing there, James?
Get shit when it's low polygon.
Yeah, but what's shit?
the accuracy of the result.
Yeah. Think about the trend that's happening.
Oh, it's decreasing.
Yeah, well now, so increase your degrees of freedom. So make your mesh size smaller than fine. So if you actually go recreate your mesh, click mesh parameters, and that top value, yep, that's your actual global mesh size. So when you change that slider, you're actually changing that value.
Yeah.
So slide it all the way to the right, and then go, so it's 3.4, make it like 3, and run that again, and then plot that as well. And you could probably do an even finer one after that, and just plot those results as well, just so you've got an even, a nicer curve, and you can really understand what the trend's doing.
It's an exponential.
Is it done? There we go. It's gonna sit and have a think.
Yeah, once you start getting into those smaller elements, even good computers start to take a bit of time. If you look at the lecture, there's actually an example of the solution for one set, like one tetrahedron, and it's quite a lot. And you can imagine you've got however many degrees of freedom now, and each one of those is represented by a matrix, and they're all affected by each other. Like the computational maths required to do this is ridiculous.
Probe. It's gonna sit and have another think. And it's hit the wrong spot. Of course it has.
It's close enough though.
There we go. Uh, 1.14 either 3.
Cool. All right, I'll run through the breakout rooms one more time, and then I'll pull you guys out.
What's happening in the other ones? Anything?
Nah, not really.
Fun.
Oh, no.
Oh, I'm forgetting to get the displacement.
How do you change the mesh size? Like how you just did that.
Oh, so you
Right click mesh.
if you go mesh, create mesh,
Oh yeah, create mesh.
and then you can plop in here. So if you go mesh parameters,
Ah yeah.
oh, I need to pee so bad. Please share, like, and subscribe if you want me to pee.
Jesus Christ.
Unable to create plot due to the requested quantity cannot be found in the result file. Oh wait, yeah, because I haven't run the study. God, I'm a nong. Sitting having another think.
Thinking.
Just thinking. There we go. That's at 2 mil. I really need to like. Oh, it's not even that bad. Actually, what's using the most?
Chrome, mate.
Of course, and Firefox.
53 instances of Chrome.
That's why I need all of my RAM.
Oh my god.
It's there. You may as well use it.
I mean, no.
It's like, you know, when you go driving, you pay for the whole speedometer. You're going to use the whole speedometer.
Yeah, sweet.
1.54 e to the 3. I keep forgetting to get the displacement.
Yeah. Well, it uses your displacement to calculate stress, so they should be nearly identical in terms of trend line. Like the plot should be the same.
Yeah. Okay, cool. It makes sense because you can see the.
Yep.
Results advisor. How many degrees of freedom?
Solve the myth.
I've hit the wrong button. A lot.
1.1 mil.
There we go.
You
Right.
change the tetrahedrons. Mr. Campbell? Sir? Oh, leave breakout room.
Oh, he left. Oh, I need a piece of bad. I'm sure everyone needs to hear that. That's going to watch this later. Oh well. Oh, breakout rooms are closing.
Mesh parameters or advanced. When you're creating a mesh, there should be a box that you can check to click draft quality mesh. And draft quality mesh is a TET4.
Draft quality mesh. Oh yeah, so. And then it's normally just TET 10.
Yes, so standard quality mesh is TET10s.
Alright, so here's
Is that everyone? Yep, everyone's back. Sweet. So, what I wanted to show you guys is the basic lesson that they've tried to demonstrate from today. I'm just going to run this study. See how long it takes. All right, never mind. Right, well, I'll run this one then. Okay. Maybe not. Better? One. All right, never mind. I don't know why that's not working. It should be. I haven't changed anything. It's very not happy with me. All right, anyway. What I've done... Yeah, SolidWorks is great. What I've done is plotted the stress at this point specifically. So I know the document asks you to plot where the max stress is, but you will notice that sometimes the max stress can be around the bolt hole as well. When you're looking to check a singularity and check that the singularity actually is behaving the way that you want it to, or maybe not. So this is again going back to that stress equals force divided by a cross-sectional area equation. At this point here, you're worried about the particular hot spot right on this corner. Now, it may be slightly above this corner, and that's because of something called nodal averaging. Now, it takes the nodes at each corner of the mesh, and then it averages those, the values at that node with all of the surrounding tetrahedrons. So what you want to do is you want to plot your degrees of freedom versus stress. You can also do this with your displacement because it uses your displacement to calculate the stress, which means your stress and your displacement should follow the same trend. Now, what kind of trend are we seeing here? Does anyone have any ideas what we should expect? Someone give me something, anything.
Parabola.
A parabola? No? So what we're seeing, what we should see is that the stress at this point here should increase and then flatten out. And that's because you should only have a finite stress. What we're actually seeing is as you increase your degrees of freedom, which theoretically should mean you're increasing the accuracy of your results, your stress is increasing. So if you have theoretically infinite degrees of freedom, you'll have a theoretically infinite stress. That means that the stress at that point is dependent on the accuracy of your mesh. Now, what should stress be dependent on? Someone, anyone?
Material.
Material, but also the geometry of the part. Force and area, exactly right. So area being the actual geometry of the part that you're designing. So if it's dependent on the mesh, which is something that you decide, then it's not dependent on your geometry, which means it's a singularity. This is the method that you use to detect singularities and decide whether or not the stress is real at that point. Because the stress that we're getting, these values, are not real. It's not a real stress. What you should see is this, it will increase slightly, and then it will flatten out, and it will hover around a certain finite stress value. And that is called convergence. This is a convergence study, and this is what you use to detect singularities. Does anybody not understand that?
So basically, you have to do this every time you suspect it's going to be a singularity.
Correct.
All right, split.
Because you might be designing something and you say, right, that's a really high stress point, and you're doing all these things to try and fix it, but it's not a real stress in the first place. So there's no point trying to fix it. Now, just as good practice, this kind of internal square edge, regardless, even if this has a very, very small fillet, you're going to get a high stress. The same equation, stress equals force divided by cross-sectional area. A very small fillet will give you small cross-sectional area, which means you'll get higher stress. It won't be infinite because you don't have a theoretically perfectly square corner, but you'll get a high stress. So as a good practice, to fix this, internal square edges should be filleted. Anyone that's made it up to the point where they're plotting the stress, feel free to fillet it and then redo the plot and have a look at the actual convergence study. You'll see that it will converge eventually. Now, another thing that I'd like to say is most of the convergence studies that you get asked to do will say do the first 3 points. I'd take it past that and go even finer just so that you can get a really good understanding of what the trend is, because sometimes the first 3 points aren't enough. All right. If you don't have any questions, if anyone doesn't want to, I don't know, ask anything else or get a bit more information, then feel free to jump out of the call. I'll stick around till 1:30, and yeah, thanks for coming. I'll talk to you guys next week.
Thank you.
Cheers.
Alright, so Campbell, would you fillet the holes as well? Because that
These
was getting
holes?
a because that was getting a high stress as well.
No, so that's getting a high stress because you fix this face and then it's trying to push down through the part. So that is technically a real stress, but the way that you've actually, this is the whole take it with a grain of salt thing.
Yeah, right.
Because you've fixed that edge, you've fixed it from translating vertically, horizontally, in both directions.
Mm.
So any of the nodes on that face can't translate in X, Y, or Z. They also can't rotate about the X, Y, or Z axis.
So
If
the
you
force is
were
going to be high.
to, pardon?
So the force will be like high in that spot.
Because in reality, if you've got a bolt going through this hole, it can translate vertically up and down the bolt, right?
Mm.
But you fix it so it can't. So the fixture that you've applied to it is not representative of a real situation.
Yeah, okay.
So that's why you're getting an excessive stress around the bolt hole. So that's why you use this as a tool, and as long as you understand small things like that, it's actually useful. Otherwise, you just start plugging numbers in and making assumptions that aren't true.
Yeah, sweet.
Yeah, so most of the time, singularities happen in places like these internal square edges, or where there's a lot of potential shear force. So you've got, so one thing you can do is if you you can sketch on a face, you can sketch a circle around the edge. So let's make this 25. And say you're trying to represent a washer, you go insert curve split line that face with that sketch. Now you've got two different faces. And now if I fix this face and apply a force to this, the nodes between these two faces, you can get a singularity right at the edge, just because of the way that it's applying force to the part. So if you understand the way that the nodes are behaving next to your fixtures or next to your forces, then you can really start to identify singularities and stuff just by looking at it. But again, you can't properly tell that it's a singularity without doing your convergence study. Not a problem. All right, guys, I think we'll leave it there. And I will talk to you guys next week. Thanks for
Cheers,
coming.
mate.
Cheers. No worries. Bye, bye, bye.
See you next week.